thanks everyone for coming back. So yeah, I wanted to continue with the discussion of sort of the setup of the geometric Langlands program. First, any questions before I start in on it?
We are glad you recall what we talked about yesterday.
Yes, because some people weren't here. I will recall some of what we talked about yesterday, but some of what we talked about yesterday was kind of technical, and I'm not going to recall it. Okay, so what happened last time? So we sort of discussed the three settings I want to discuss in these lectures for global unramified geometric Langlands correspondence. So the first was the Duram world, where we deal with D modules as our category of sheaves. The next was the Betty world, where sort of sometimes write this as all sheaves, or maybe all sheaves with they'll put in singular support is the category of sheaves. So these are just sort of sheaves for the complex topology. And the last was the Ital world, where I don't know, Ital sheaves are sheaves, but usually I just call them sheaves. And then we introduced the Hecke symmetries at the end of the talk. And so, again, briefly, the sort of naive setup would be that you say that for every x and x and every representation of G check, then you get this corresponding Hecke functor from sheaves on bun G to sheaves on bun G, so to say in any of the settings above. And if you have an n-tuple of points and representations indexed by the same points, then you get sort of some kind of thing you can compose. So this is sort of the composition, and the order doesn't matter. So this was some kind of endofunctor, and these kind of compose in a certain way, where if the points are distinct, there's nothing you can say, but if the points are together, then you can sort of collapse two representations into their tensor product. And I also said that you can sort of take a construction like this, you could weight it by a constructible sheaf, so to say, in the variables x1 up to xn, or just any sheaf in the variables x1 up to xn, and then kind of integrate that out. And so there's this sort of souped up version, which was that there was some kind of source category, which we called rep g check ron, and this acted on sheaves on bun G. And so this is the place I wanted to start the discussion today. So, questions? Was that a sufficient recap? Okay. Okay, so now I want to start discussing spectral actions. And so so say in kind of in any in any of these contexts, so remember I had spaces of local systems for each of these. I have a a symmetric monoidal functor that plays an important role. Which we call loc spec. And this, just because the notation in the subject has to be really off-putting all the time. And so this loc spec goes from rep g check run into this category of quasi-coherent sheaves on loc sys, well, g check. So far, it's not really anything about the dual group. And this is sort of question mark. So we had these various symbols that go here, and this is appropriate to our setting. And let me first state the intuitive idea. So kind of like on that board over there, if you have x1 up to xn, some kind of points of x, and you have some representations, then this gives rise to some kind of object. I'll write a little bit formally like this. Inside of this let me not write it that way. I'll write it as the sort of convolution product, the tensor product. So this is the. So there's some sort of associated object inside of this rep g check run. Namely, if you think just I have an object for each one of these points labeled by a representation, and then I can tensor them in rep g check run, which is a symmetric monoidal category. And so this is sort of the object that gives rise to the Hecke functor I wrote over there. Not sort of. This is the object that gives rise to that Hecke functor. And so I can take this object and I can ask what's the corresponding quasi-coherent sheaf on loc sys g check. And then the point is each xi is going to give rise to a map from local systems on x to local systems kind of at this point. What are local systems on a point? They're all trivial, right? That's what we learned in algebraic topology. It's just a point, right? No, but they're not canonically trivial. And so this is actually a copy of the classifying stack, BG check. Yeah? So I'm saying just kind of like, imagine the group is GLN. So if you have like a locally constant, so a point of B GLN is just a vector space of the given dimension. And I'm saying that if you have a local system on X of rank n, then you get, for each point, an n-dimensional vector space. And it's just taking the fiber at that point. Very simple-minded construction. And so then that's going to give rise to a functor from rep g check to quasi-co of loc sys g check of x. And this is called sending v to the corresponding evaluation bundle, I guess vi, which we sometimes write evixi. This is the evaluation bundle. So then, of course, I just tensor these. OK, I feel like if I were giving this talk in America, I would just stop here. But in France, I always feel like I have to write all the formulas very rigorously. And so more formally, so let me remind that rep g check run was designed to receive functors from rep g check tensor I, tensor sheaves on x to the j, and let me just put I, for every finite set I. So some kind of co-limit so that there were sort of definitional functors like this. And really, there's for every map, but they're all designed. These ones are sort of generating. So you have to think about the I to j's when you say the compatibilities between the functors. But let me not do that level of rigor in a lecture. OK, so what I need to tell you well, OK, so I need to provide functors from here to this quasi-co of Loxis G check. So so the input is that there exists a tautological functor from this quasi-co of Loxis G check. Where is it? From rep G check, there exists a tautological, let's say, symmetric monoidal functor into these sheaves on X. And this is basically, so let me just kind of explain how this works. So in example 1, Loxis G check. OK, so this is the de Rham setting. So this Loxis G check de Rham, well, it was the space of maps from this X de Rham into BG check. So this is this sort of space where you take X and you identify infinitesimally close points. And it's designed so quasi-coherent sheaves on here are D-modules on X. And so that tells you that there's a canonical map to here. And then by pullback, you get a map from representations of G check to quasi-co of this X de Rham times Loxis G check de Rham, which is the same thing as oh, I'm supposed to write it in the other direction. And so just intuitively, what's happening here? So I'm starting with a representation of G check, and then I'm forming some kind of sheaf on kind of Loxis G check times X. So that means every time you give me a local system and a point, I'm supposed to form some vector space out of that data. And so what I do is I take my representation, I take my local system, I twist it to get a local system on X, and then I take the fiber at the marked point. So that's what this is expressing. Questions about that? So so examples 2 and 3 are in the Betty and Ital worlds. Actually, I have a functor here from rep G check to quasi-co of Loxis G check tensor local systems on X. And Loxis G check was actually essentially defined. Well, it was defined in the Ital world. To be universal for receiving such a functor. So this is kind of a Tanakian picture on what Loxis is it's sort of the thing that receives a symmetric monoidal functor like this. And it's always, I should say, right T-exact functor. But it's OK, questions so far?
So is there any problem to replace classical with equal Loxis?
For this construction? There's no problem exactly, but So quasi-co lives inside of int-co, and if you do this in the int-co world, then you'll land in quasi-co.
I see.
Yeah, in some sense this is one of the difficulties of the subject, actually, is that it's which just to be clear why that is. So like, what we're doing here is we're sort of, I mean, I should say.
So is it because the finite dimensional guy are all map to public complexes?
Yeah, that's kind of intuitively what's happening here. At least when you take the fiber at any point here, you get something perfect. So it's like, yeah, so you can think that we're sort of, I guess what we're kind of trying to do with this construction in some ways is take this thing, which is not sensitive to like really the global issues with X. It's, I mean, like, it was a construction that made sense for any curve. It didn't have to be a global curve by any means. It's somehow, it knows stuff about the, so to say, the topology of X, but it's, you should think of it as kind of something of local nature, and you should think of this space as something of global nature. And we're kind of trying to, in some sense, like, integrate, I don't know how to say it right. So this is some kind of local to global procedure, this localization that we're doing. I guess that's the way we think about it. And you can say one of the difficulties in the subject is actually it's very kind of hard to get to int-co of locus by local means. We can get to quasi-co by local means. And this is somehow one of the repeated issues. OK, so yeah, so I have these functors, and then what do I do if I'm being very rigorous about everything? So then OK. Well, so I can take, if you give me an I tuple of representations and a sheaf on x to the I. So now what I can do is I can map this. Let's see, what do I want to call this? How about I'll call this the evaluation map. It's sort of some way of forming universal, like some evaluation bundles, maybe evaluation star. No, that's fine. So I can sort of run this this functor I many times. In fact, well, really, not even here. It doesn't make a huge difference. Then what I can do, so this is sort of, again, forming like, think of like I did nothing along this factor, which again was sort of encoding the measure that I integrate along. And then along this factor, I just form sort of the I tuple of universal evaluation bundles. Now what I'll do is I'll tensor along the first factor. To get down to just a single copy of quasi-co of locus g-check tensor these sheaves on x to the I, tensor with these sheaves on x to the I. And then I'll do the identity. And here, I'm going to pair these. So that means that I take sort of cohomology of x to the I with coefficients in the tensor product between these two sheaves. And that'll take me down to quasi-co of locus g-check. And so that's like, why did I do the tensoring? That was because I tensored all of these evaluation bundles together. So if you just sort of unwind the intuition, then you get the commutative diagrams out. So, questions? Okay, so the first spectral problem is the following question. So does the action of this rep G check run on sheaves on bun G factor through an action of quasi-co of Loxis G check in the various settings. I guess I should also say, okay, I'll make a remark about this in just a moment.
Yeah. But these blues vector bundles, how far, what do they generate inside Q-co?
Great question. I'll come back to that in just a second. Yeah. It's a satisfying answer. But so let's imagine for a moment that it's a well-posed question, which it actually is. That's what I'll say. So what's the intuition behind this? The intuition is sort of that if you imagine trying to kind of diagonalize this action in some sense, that's like trying to diagonalize all of the Hecke operators in automorphic theory. And so this is saying that kind of any Hecke eigenvalue should really kind of come from a point of Loxis G check, which is the sort of thing that the Langlands philosophy tells you. There's no eraser. Oh, here's one. Here's a better one. Okay, so first is a remark, which is that this Lox spec is actually a quotient functor. In the Betty and Durham worlds, it even admits a fully faithful adjoint. So the spectral problem is well posed. Okay. Okay, the hard part about it is that I find it difficult to express the proof without the language of chiral algebras. This is like the kind of thing that chiral algebras are very good at. But
in the restricted setting, I mean, in this, when you consider LS, the restricted LS, then it's quite explicit, I guess.
It's quite explicit. So, yeah, and you don't have to say it in terms of chiral algebras.
So in that case, the proof is easier?
The proof is... I would not say that the proof is easier. It's not that it's an especially sophisticated proof or something, but it's I mean you can just sort of mimic certain constructions that were first done in the in the D module setting. But so it's to say it's not that it's a super deep proof or something, right? There's no Langlands duality in this assertion. Yeah.
You can construct some explicit generators from the functors.
Explicit generators for this quasi-Coloxis G-check. Yeah, absolutely. You just take a bunch of representations. So fix a finite set I, fix a bunch of representations, then do this localization procedure to sort of take your I tuple of representations to this sheaf on loc_sys, tensor by some like Lee's sheaf on x to the I, and then you tensor by some constructible sheaf on x to the I, or some d-module maybe on x to the I, and then integrate out along the x to the I factor. Those will all be compact objects if the sheaf on x to the I you started with was compact. And so those give you compact generators that are reasonably explicit for this. Yeah. So the idea is that they're all obtained by sort of suitable integrations of these evaluation bundles.
And is that like very easy to see that they are actually generators without going through chiral algebras?
Again, you don't really need chiral algebras. I mean, maybe everything that's coming up is like a commutative chiral algebra. So it's not really a deep problem. It's just like that's where it's in my brain. I do not know offhand a shorter proof that those objects generate than the proof that it's actually a quotient, I think. Yeah. Other questions?
How about the Étale setting?
In the Étale setting, it's a quotient functor, but it's not. It doesn't have an adjoint. Yeah. So sort of the best situation for a quotient functor is when it has a fully faithful left or right adjoint. But that's not always the case. It's related to the fact that, like, see if I take the unit object in here, that's a compact object, and it goes to O inside of this loc_sys G-check. And O is compact for any kind of reasonable algebraic stack and characteristic 0, which I am. And on the other hand, this loc_sys in the restricted world, I said it had some formal directions, and O is not compact on formal schemes. So it's this kind of thing. Yeah, that's part of that's how you see the difference, I guess, between the two. Other questions? Okay, so now I want to state the answer to the spectral problem. So example 1 is the de Rham setting. So here, there's a theorem of Drinfeld and Gatesgory that says the answer is yes. So just the spectral problem is a yes or no question. The answer is yes. This rep G-check run action factors through action of QCO of loc_sys G-check de Rham. So this is kind of reciprocity for Hecke eigenvalues. Okay, so in examples 2 and 3, there's a theorem which is due to sort of Nadler-Yun in one direction, and then maybe this AGK RRV, or maybe some parts of it are kind of a subset of, okay. But the theorem says that in the Betty and étal worlds, this sheaves nulp on Bun-G inside of sheaves on Bun-G is first of all stable under the rep G check run action. And is the maximal subcategory on which the spectral problem holds, on which X through quasi-co of this Loxis G check. Question mark. So in other words, you can take this rep G check run mapping to this quasi-co Loxis G check. You can take the kernel, that's some kind of ideal inside of here, and you can take the subcategory annihilated by that kernel, and that'll be exactly sheaves nulp. And so you can take this as a definition. So I said that I would give a better definition of this sheaves nulp at some point, and for like many of the arguments in the theory, this is the most convenient description of sheaves nulp. It's not always the case. It's great to have this useful, so to say, topological description of the category also, but well, not everyone likes singular support, and then this is telling you which category I'm actually talking about.
But the proof that using the singular support condition that sheaves nulp is invariant under the rep check run, that's supposedly not so hard, is it? Or
not so hard. Yeah, you just kind of have to.
Compatibility of Hecke operator and singular support.
Yeah, right. I it's one of those things. I just wrote this not because it's like the essence, but just kind of so that what follows makes sense. But you can think of that as there's sort of three statements here, really, if you unwind what's really going on. And one of them is the statement you just made. Another one is that if you start with something in sheaves nulp, like as defined by singular support, and you apply this like Hecke functor to go to Bun-G times X, then you get something which is built from like sheaves on Bun-G times local systems on X, like box products. And so that's basically what Nadler and Yoon prove. And what's proved here is kind of essentially the converse, that if you have that property under the Hecke functor, then you actually were in sheaves nulp. And so, yeah. And maybe let me comment that also when I'm in the étal setting, it's just occurring to me, my P is sufficiently large. It's a very small bound on what P actually is. Like for GLN, P is bigger than N most of the time, but okay.
And is that bound explicit?
Yes.
But why is the bound there?
The bound is there because, like, I think that, for example, for SL2 and okay, I hope no one comes after me, but I think for SL2 and characteristic 2, it's not known that the nilpotent cone is like Lagrangian. It's like, and I think it's yeah, this kind of thing. just nilpotent elements are really badly behaved in very small characteristics.
And the important cone where in T star, sorry, which important cone in the Lie algebra?
In T star, well, in the Lie algebra, but also in T star bungee, yeah. That's the one that I don't know if it has the right dimension. If I ever knew.
Oh, even the dimension bound is not known, you're saying.
The what?
Even the dimension bound of the.
No, it's just that I didn't prepare for the talk. There's a. I don't. It's not literally known to me at this moment. Yeah, even the dimension bound. It might. It's probably known to science, but it's just. There's a paper by Faltings where he thinks about sort of very small primes in exactly this context, and I don't remember if. I think he might, for example, for SL2 say that for p at least 3, it definitely has the right dimension. And my memory is he doesn't answer the question in that paper, but it's just. Yeah. Other questions?
So what you're saying, except for the dimension, it's Lagrangian. If you know.
I'm not saying that. Yeah, and I'm also not. Yeah, the proof works in the setting it works in. It's just that there's like the first thing that falls apart is that the nilpotent cone is not as well behaved. Okay, so this is some sort of characterization, and let me sort of say, actually, moreover, in the de Rham setting, this category of D modules with nilpotent singular support on bungee is the maximal subcategory on which this quasi-co of Loxis G-check de Rham acts through this quasi-co of Loxis of G-check restricted. And so this has funny consequences. So, for example, I want to claim the following. Okay. A corollary is the following. So, the category of D modules on bungee is generated by the following categories. So, take D modules with nilpotent singular support. So again, this is a category that allows all non-holonomic D modules. This nilpotent cone is again some Lagrangian, as we're discussing. It's some Lagrangian. So these are all holonomic. In fact, they have regular singularities and things. I'm going to take bungee, but then I'm going to write K prime for all field extensions K prime over K, so maybe transcendental.
Are you going to explain how this statement makes sense, like how it parses?
Well, okay, first how it parses, what's a D-module? It's something like a module over the Weyl algebra. So if you have a module over like the Weyl algebra for C, you can restrict it to a module for the Weyl algebra over Q. So there is a restriction functor from D modules on bun G K prime to D modules on bun G.
Yeah. Okay.
Does it make sense?
Well, I guess so.
Yeah.
Parsing.
So for any y, let's say over this field K, and any K prime over K, so if I take this category of D modules on y base change to K prime, this is going to be the same thing as taking the category of vector spaces over K prime, tensor over vector spaces on K with D modules on y. This is just a fancy way of saying, like, take basically the category of D modules on y. This is enriched over K vector spaces. Now just start tensoring those Homs up to K prime to force it to be enriched over K prime vector spaces instead. So this is some kind of tautology, like I was just saying about the Weyl algebra. And so then there's, kind of functors of tensoring up and forgetting, which in this business we call oblivion, after Dennis. And so what I'm saying now, but let me just say that this obliv does not at all preserve things like holonomicity. Kind of, in fact, if you stare at if you've looked at D-module theory before, then one of the first things you learn is this B function lemma, and this is part of the mechanism of the proof of the B function lemma. Actually, is you go to this transcendental extension of your ground field and play some games up there that kind of don't make sense downstairs because of exactly this sort of thing. Yeah.
If you took a smooth variety, would you have a similar statement about D modules on that variety, but where instead of course you don't have milk, but you could say holonomic or something?
Let me think for a second. So, I don't personally know that statement. So D modules on GM, it's okay, and you can take Lee's guys. But I know that for funny reasons. I think for
Is it easy to see how to get D exits?
Yeah, it's probably true by reduction to the case of GM. It's not easy to see how to get dx itself. Yep. Yeah. So here's the proof. So so this quasi-coev-Loxis G-check Durham, you can see is this is some sort of general thing with Cousin complexes. It's generated by skyscraper sheaves at points, but maybe let's say at field value points. But allowing possibly transcendental extensions, like the delta sheaf at the skyscraper sheaf at the generic point I count as one such thing. So say I have a local system sigma. Let's suppose that I take this as a K prime point. So I take the corresponding skyscraper sheaf. Let me call it delta sigma. And then I act on, well, okay. Let me give a definition. So I write p sigma for the Hecke operator. Well, I do this in all settings. Which is the action of the skyscraper sheaf. So because this category is generated by skyscraper sheaves, d mod of Bun-G is generated by the images of all p sigmas. But now if I take this p sigma, kind of by design, it was really happening over this k prime. So this is my p sigma. This is my d modules on Bun-G over this k prime. So nope, it's the forgetful functor. This is the lift. And moreover, by design, it maps into Hecke eigensheaves. For sigma. I didn't exactly say what Hecke eigensheaves are, but okay. Well. Let me still say it this way. Now the point is that sigma is a point of this Lhoxis G-check restricted of x over k prime, but it's not a point necessarily inside of this Lhoxis G-check restricted of x. So it's again like this sigma again. Think of it as it's what it is. Like let's say the group is GLN. It's just a vector bundle with connection on x, but defined over k prime. And that's exactly the kind of thing that gives you a point of this Lhoxis G-check restricted. But then when I restrict that vector bundle with connection, I might get some huge non-holonomic kind of thing on x. And so it doesn't count here. And so then I'm saying that actually, sort of like by that theorem, it's going to factor through this d mod nilp. Yeah.
Are those generators the same that compactly generated?
No, unfortunately, these guys are not at all compact. So it's sort of like if you just think this, the kind of thing I'm doing here is taking like the skyscraper sheaf at the generic point, which isn't a compact object and quasi-co-Lhoxis, so no reason to think it. Yeah. Yeah, sad. Yeah, so it's a sort of bizarre procedure a little bit. Let me just make a couple remarks here. So, so the same works in the Betty setting. So, namely, sheaves nilp all. So you allow these. So let me emphasize for a second. I'll deal with E coefficients. So I allow infinite rank local systems with nilpotent singular support. I allow weakly constructible sheaves with nilpotent singular support. And this is generated by this sheaves nilp, not weakly constructible, but honestly constructible on Bun-G but I allow E prime, and this is for all E primes over E. With, again, the same property that if you start with, let's say, just in topology, if you have a local system of E prime vector spaces, maybe it's a finite rank local system, but then you consider it as a local system of E vector spaces, it doesn't have to stay constructible. It may just be weakly constructible. So the philosophy here is that if you're working over a field of characteristic 0, then you have the sort of equivalence principle that sort of this de Rham geometric Langlands conjecture is sort of roughly as hard as this restricted geometric Langlands conjecture, which is just as hard as this Betti geometric Langlands conjecture. So this is sort of I'm extrapolating a little bit more than what I said here. Here I formulated some precise statement, but actually you can sort of apply this sort of logic to really extract this kind of thing. So the idea is that you can really kind of just, if your goal is to understand this category of D modules on bun G, it's really enough to understand D modules nilp bun G K prime for every K prime. For example, in the context of the geometric Langlands conjecture. And so this is one of the, so it's sort of like if there are like 3 elevators for the 3 kinds of geometric Langlands, then you don't know which one you're in or something. And I want to point out that, yesterday we were talking about kind of these strange objects that come up in the de Rham world or in the Betti world. And one perspective a person could have on the subject is that those strange objects, you don't necessarily need to take them as essential in the subject. You can view them as coming just by restriction of scalars from this restricted geometric Langlands conjecture.
There are stuff that don't work as well in the Betti DMC, like
What's the question?
it's equivalent? Really,
So I'm what this means to me. Okay, it's not a precise mathematical statement, but what it means to me, it turns into a precise mathematical statement, which is that if you know with a certain level of knowledge any one of these 3 conjectures, then you know the other 2.
Ah, okay.
So for example, so like a priori this de Rham world and this Betti world feel like very different stories, but actually you can sort of pass through this intermediary which talks to both of them, and it's just, so this is about infinite rank local systems, this is sort of about finite rank local systems, this is about possibly non-holonomic D modules, and in fact you can sort of reduce the non-holonomic guys to these finite rank local systems, which you can also stick into this world. And this world, these infinite rank guys, you can reduce to finite rank guys over extension fields. Yeah. So yeah, just by this simple procedure that kind of the generic point or any K prime point is really a closed point over of when you base change. It's this kind of mechanism. Other questions? Okay.
And how does the étal relate to it?
So the étal relates to it because, okay. So étal in characteristic 0, yeah, it's also like. So I guess I'm being like a little bit sloppy here. So when I say this restricted thing, I guess I want to say, when I talk about restricted, I'm sort of dealing with some notion of constructible sheaves or something, right? So this restricted de Rham geometric Langlands conjecture, maybe a better way to say this, is that this is somehow equal in the special case when k is equal to c, and I guess my coefficient field is also equal to c, to this restricted Betti conjecture, which then is sort of equivalent to this big Betti geometric Langlands conjecture. And in some sense, you can sort of think that the étal restricted geometric Langlands conjecture is contained inside of here. So if you, yeah. Because there's strictly fewer étal local systems than Betti local systems. So it reduces to that case. All of that needs a little bit of like checking and explanation. That's slightly beyond the level of what we've said so far, but that's the message. Okay, other questions? So I need to say one sort of brief word about Whitaker coefficients. Let me be in the de Rham setting. Okay, so the statement is that there exists a certain, okay, it's a construction of a certain functor, which I call coef, from these sheaves on bun G to the category of vector spaces. And what you should think is that this is the analog of sending, it's the analog of the map from sort of modular forms, holomorphic modular forms, to C, sending some f, which is maybe a sum of an q to the n. I'm just going to send it to its first Fourier coefficient. Which itself is some kind of integral of f of tau e to the minus 2 pi I tau from 0 to 1. That seems right. So it's just to say, you take the function and you integrate it against some exponential. So in the geometric setup, trying to express if this is the upper half plane, I'm just integrating my function against the exponential character from here to here. So in the geometric setup, what I do is the following. So okay, so I form bun G. So this is kind of the analog of the upper half plane in this picture. And then I form bun N, and there's going to be a slight twist that comes up in the bun N. let me call this map Pn. And then there's going to be a character, sort of exponential character here. And this this bun n, like I guess one thing you can sort of, well, if n is GA, then sort of in the comparison with modular forms or something, then the adelic quotient here is something like R mod z. So that's sort of our circle that we're integrating along, just for what it's worth. That's not essential knowledge. I'm just sort of mumbling things to myself. So so what I'm going to do is then I'm going to take this Whitaker coefficient of a sheaf F, and this is going to be the cohomology of this bun n omega with coefficients in this pullback of F tensor by the pullback of the exponential. That's going to be a formula, but then I have to explain the meaning. But the idea is that here I'm sort of integrating. This is sort of my analog of the circle. This is my analog of the exponential character. And this is sort of just restricting my function to the circle, so to say. And so what's the setup? So OK, so let me tell you what the various symbols are. So so this bun n with no twist, you can think of it as a B bundle whose induced T bundle is trivial. I guess maybe I should say at some point that n, this is a Borel, and this is the it's radical. It's unipotent radical. Nope. And T is B mod n. And then this bun n omega, it's basically the same thing, but you realize that you're supposed to include a twist, which is by row check of omega. So here, row check is OK. 2 row check is the map from GM into G check, or even into T check, which corresponds to the sum of the positive co-roots. And then row check of omega, by definition, means 2 row check of the square root of omega, where one of the secrets is that because omega has even degree, I'm allowed to choose the square root of it, and I secretly chose one before the discussion started. So as an example, if G is SL2, then this bun n omega is, well, bun n will be the set of extensions, the stack of extensions like this, and bun n omega is going to be the stack of extensions like this. And this is sort of isomorphic to, you want to say H1 with coefficients in omega 1, but it's kind of that I take this this complex. So normally if I have a, let's say, finite dimensional vector space, I can turn it into a scheme in some very simple way. And if you have a complex in degrees -1 and 0, you can think of it as a stack. And so I'm just going to do that, and this is the same stack. And now let me tell you what the character is in this case. So the character psi is going to map to H1 because the complex maps to its top cohomology. And this is equal to A1 by Serre duality. So in general, each simple root, each node of the Dinkin diagram, gives rise to a map from n to GA, and therefore to a map from this bun n with the omega twist to actually bun GA with some twist. And if you think what this twist is, it's going to be sort of, I should say, it's like this kind of, I do like alpha I composed with rho check applied to omega, which is this exactly this bun GA omega, which is the same R gamma omega 1 with the shift by 1, which then has this character psi I down to A1. Maybe let me call this psi I. And then psi is equal to the sum of the psi i's, where I sum over all of the simple roots. So this is the standard kind of construction called the Whitaker construction. And if you've looked at reductive groups a lot, you've surely seen this many times. And if you haven't, then it looks a little bit strange. But it's basically, this is what people say is kind of the right analog of a Fourier theory for non-abelian groups, of Fourier coefficients. Is in the case of GA, you can sort of convince yourself that this is like the right notion of like first Fourier coefficient. And in general, what people say is that you should sort of take this maximally non-degenerate thing. Okay, and then most of the formula up there is explained. So I guess this Pn is sort of clear. So there's always a vector bundle in the middle of the extension. That's my SL2 bundle. Or said a little bit better, this bun n omega maps to bun B, which maps to bun G. And then this guy exp is the following D module. So it's O on A1, and then I give it the connection, which is D minus dt. And this is the algebraic differential equation, sort of f prime equals f. So if you think about D modules as algebraic differential equations, this is the equation for the exponential function, which doesn't require anything analytic in order to say. Okay, so that's a construction. Questions about it?
So this has a micro-local. I remember last year we talked about another way to define this.
Yes, in the Sheaves-Knope world. Yeah, it has it's some kind of microstock. But yeah, there's a lot that's fun to say about it. And I sort of gave that talk here in Paris. So I think I'm not going to, I thought about whether to do it again, but. Okay, and so let me just kind of comment that in the Betty and et al. Worlds, you can also make sense of this. So basically the way it'll work is that you'll take this bun n omega, then I'll quotient by some kind of GM, which is acting essentially through rho check. This now maps to bun G, and this now maps to A1 mod GM. And so what I'm going to do is I'll do pull and then push to this A1 mod GM, and then I take Hom from J lower shriek of the constant sheaf on sort of GM mod GM on the point.
Is that A1 mod GM with GM acting by a usual scalar or like the square of usual
It's a very fair question.
Maybe it's not appropriate for the level of the lecture.
No. It's just it's completely appropriate. I just let me sort it out again and get back to you. I've been confused about this before, but also there's a bigger issue, which is that it's like this. And so this is sometimes called the Kirillov model for Whitaker coefficient. So it's a way of getting around the non-existence of the exponential sheaf in general. Okay. Okay, so the role of this Whitaker coefficient. Okay, so one of the basic expectations in the subject is that, for example, well, in any setting, when you do this sheaves, maybe with some decorations on bun G, and you say that this is equivalent to some kind of coherent sheaves on this locus, then I have this coefficient functor to vector spaces. And this is supposed to correspond to the global sections of locus over here. And this is what people call the sort of Whitaker normalization of geometric Langlands. So the idea is that, like in the classical theory of modular forms, if you think about what the Hecke eigenforms are for a given, well, okay, if you take a Hecke eigenform, it's clearly only normalized up to multiples by scalars a priori. But the usual normalization people take is they force A1 to equal 1. So it turns out that essentially always works. You should, besides for like the constant function, that uniquely pins down a representative in each eigenspace. And so that's sort of what this diagram is expressing, is that a priori the Langlands equivalence is, we'll see that this coefficient plays an essential role in characterizing it. And you should think that if you're kind of trying to diagonalize the spectral action, you can think of like picking out a Hecke eigensheaf for each local system, roughly. And that's only going to be normalized up to maybe tensoring by vector spaces or cohomological shifts or tensoring by lines, let's say. And this tells you kind of a unique representative that removes that ambiguity of, let's say, tensoring by lines.
So abstractly, so both of the so either side is like a canonical module over this quasi-co on locus G check. But is it known that abstractly that the endomorphisms of either side as a module over that category is the same as line bundles? I mean, invertible objects in that category? Automorphisms, sorry.
Okay, so you're saying are automorphisms of int co nope locus G check, which are okay, you're saying take automorphisms of this category that are linear over quasi-co, then yeah, it'll send co to co, and it'll send perf to perf, and so then it's given by tensoring by some line bundle. Yeah.
Okay.
Yep. Which is pretty mild in the Duram and Betty worlds, and somehow pretty serious in the restricted world. Yeah. Yeah. But maybe just to have kind of a toy example, I think, for what this sort of Whitaker normalization is saying is, a nice one is when G is equal to Gm. So in this case, we're talking about some kind of sheaves on Bun Gm, and then this is supposed to be equivalent to some kind of quasi-coherent sheaves on some sort of local systems for Gm. And this, in practice, is always given by a Fourier transform, sort of categorified Fourier transform. And then what this coefficient functor is you take the fiber at the trivial local system. So if you just run this algorithm, then you'll see everything was trivial in what I said. So this bun n is just a point in that case. So I pull back, and then I kind of do nothing. The character is just mapping down to 0. That doesn't change anything. So that's mapping down to vect. And over here, I'm taking global sections. And so this is sort of saying, like, if you think about the Fourier transform as like a spectral problem about kind of diagonalizing some operators, then basically the fact that sort of evaluation at the unit is Fourier dual to like summing over the dual group, that's the thing that normalizes the spectral problem. And then there's I would say, in some sense, a serious point, which is that this actually generalizes to non-abelian groups. And that's.
Sam, sorry, could I ask her just a refinement to my question? So then, is it true then that the space of, the automorphisms of the pair then consisting of the Q collinear category together with the vect linear global sections functor, that automorphism group is trivial?
Yeah.
Okay. And is even contractible?
Yeah, sort of. Yeah.
Because then you get a linear functor a linear functor to linear functors from Q code vect. And that's basically okay.
Yep. Yeah. So I mean, this functor is like dual to an object here, and that object is O, and so I'm saying that if you had this ambiguity of tensoring by a line bundle, knowing who O is, it removes that ambiguity. Yeah. Yep. Other questions? Possibly also from Dustin. Yeah. Okay. So now I want to talk about the construction of the geometric Langlands functor. Is that what I want to say next? I guess it is. Okay, so no, I want to make one other remark, and then I'll come back to this. Just psychologically. So, so in the Duram setting, I'm going to define the Poincare sheaf to be kind of given by the dual operation here. Psi upper star of this exponential. And so this co-represents this coefficient functor. So Ham out of this Poincare sheaf is the coefficient operator. So sometimes this gets called the Whitaker sheaf also. I don't know. There's a choice of normalization in the terminology. In the Betty world, then I take sheaves nulp of Bun-G, sort of this all object. And so this embeds into sheaves all on Bun-G. And sort of just like in that game, I can make sense of the Poincare sheaf here. Maybe let me call it the big Poincare sheaf for a second. And then it turns out that this embedding actually admits a left adjoint. And so I can apply my left adjoint to this Poincare shriek big, and I'll get an object. Let me not call it big. Let me do this, and then I'll call this nulp. And you can do something similar in the étale world. The adjoint actually, it's a right adjoint instead. But which is confusing, but I don't make the rules. So yeah, so this object is going to be, again, what corresponds to O under the geometric Langlands equivalence. So that's sort of just a dual statement here. It's like the thing that co-represents global sections is O. And it's convenient to think about. And let me just say one of the, maybe for future reference, one technical point one point that's kind of trivial and also important is that this Poincare sheaf in the de Rham world, it's very simple to understand. Look, here it is. It's given by this formula. Like I know what that is as a geometric representation theorist. And in some sense, this object is very difficult to wrap your head around. It's like a very, very complicated object. So. Questions?
Why?
Why what?
Why is one easy to understand and one difficult? I mean, can you?
Yeah. I mean, okay. Sorry. So like this object is just as easy to understand as that object. They're kind of the same, but like
because of this left adjoint.
It's because of the left adjoint. Yeah. So like in the case of like GM or something, it's like talking about the skyscraper sheaf at the origin.
And then you convert it into a local system.
Then you convert it into a local system by some procedure, which is okay. Like I can wrap my head around that because it's abelian. Yeah, but then you turn it into a sheaf with nilpotent singular support, and already the Poincare sheaf itself is a little complicated. And so, yeah, then it's just like, I don't know how to like compute with the result anymore or something. Yeah.
Even in GL2, SL2, something like that, for small rank groups.
For small rank groups, I mean, it's not a well posed. I mean, I'm saying something. I'm making a complaint which is not exactly well posed. It's just like I don't know how to directly compute something. But that for me, it really means I don't know how to prove some particular statement that A equals B directly. Even for GL2 and SL2, I can formulate a statement I don't know a direct proof on.
So I mean, there's no easy characterization of this object, even for these groups.
I don't know what easy is or explicit or something. I mean, there are reasonably explicit descriptions, but for me they're not. They're still quite complicated. Yeah. like, yeah. Yeah, so okay, so now I want to talk about this construction of the geometric Langlands functor. So here's the sort of the theorem. So first, maybe let me do it in the. We say it for D modules. So there exists a unique. Well, okay. The construction. So first, we're going to give a functor, let's say in the D module world, from D modules on bun G to a quasi-co of loxus G check. And we call this the coarse Langlands functor. Coarse because it's not supposed to be an equivalence. It's supposed to have some kernel. This is this quasi-co versus int-co business. And so here's the idea. So in this categorical world, you can talk about duality. You can talk about duals for categories. So I've been writing this tensor product sometimes. And just as soon as I have a symmetric monoidal structure, I can talk about duality. And for reasonable stacks Y, quasi-co of Y is self-dual, which sounds like an abstract statement, but it's quite explicit. Well, if you haven't seen this stuff before, it sounds abstract. Let me just very quickly say how it works. So, so if you want to go from, like a duality means I should give you an inner product, and so this is going to send a pair of sheaves to global sections of Y, coefficients in F tensor G. And in order to check that the duality is not degenerate, it's usually good to give a co-unit also, sort of co-evaluation. And then the observation is that, again, for sort of reasonable Ys, this category is just the same as quasi-coherent sheaves on the product. So it's enough to give you just some object of quasi-co of Y times Y. And this is going to be delta star of Y. Delta star of O. And the idea is that, like, if you imagine Y was a finite set and you replace quasi-co with functions, then this is exactly, these sorts of formulas are exactly the just, like, this is, so this is just somehow the formula for the dot product. And yeah. And so it just works. And so what that means is that giving a functor LG coarse is equivalent to giving a functor actually from quasi-co of loxus G check Durham tensor D modules on bun G to vect. And so the one I'm going to choose is the following. So I take the spectral action. And then I take this first Whitaker coefficient. And so that gives me a pairing from here to here, and therefore a functor like LG coarse. So if you unwind a little, this LG course is really the unique quasi-co of Loxis de Rham linear functor, so that the following diagram commutes. So basically the diagram that I wrote up there. So in other words, like there's just some kind of general formalism. It's like very concrete mathematics that maybe comes out sounding a little bit abstract, but it's really just saying like the two ingredients I've told you so far about geometric Langlands are enough to characterize this coarse functor. It's somehow exactly the data of a coarse functor like this. So there was this spectral action, and then there was this functor, and then it uniquely lifts. And if you think about quasi-co as not that different from int-co, which I encourage you generally to do, then we're almost there. The more precise statement is that there's a sort of theorem which is pretty mild, just when you're wrapping your head around these things. So that there exists a unique functor to int-co. I'm going to put nope, but it doesn't matter. It could have been int-co also. The same statement would work. It's just not really the Langlands functor. I just want to give a feeling for what's happening. Okay. There exists a unique lift like this. So this is this projection down to quasi-co of Loxis G-check that we discussed last time. And this is this LG course. And this is supposed to have the property that compact objects, so to say small objects in D modules on Bun-G map to bounded below objects.
Do you need to explicitly say that it's Q-co LSG check linear, or is that going to be automatic?
That's going to be automatic. Yeah, because like the linearity, it's just about perfect complexes here. Can't fail. Yep.
But if you said that linearity, would you then be able to remove your subset?
No.
No? Okay.
Well, I mean, maybe like super a posteriori. Okay, so, but, okay, here's what I'm saying. So suppose you had an equivalence, just someone hands it to you. So you can take compact objects in like D modules on Bun-G. Those are going to map to compact objects here. In particular, they're like just some coherent sheaves. They are bounded from below. So that's the way I think about this assertion. Is it's just saying like, if you want a functor that sends compacts to compacts, then there's only a unique possible way to fill in the diagram. But I'm saying something more like stupider, which is I don't need to know it sends compacts to compacts, which kind of saying like it's now a well-posed question. So basically just knowing this LG course, I want to say, it's a well-posed question. So you take compact objects and D modules on Bun-G, those map to some objects here. I want it to map isomorphically onto this co-nilp that we talked about yesterday. That's what geometric Langlands says at this point. And I'm just sort of rephrasing that in terms of big categories. And I'm saying that in order to get the functor at the level of big categories, I need to know somehow very, very little. I need to know something like, proving the existence, you really do have to do some kind of actual cohomological estimates with these Whitaker coefficients of sheaves on Bun-G. But so there is something to prove here. That's what the content is. Yeah. Yeah.
It illustrates that subcategory of D models with given singular support, which is not a one-point cone, but some subvariety of it. Is there a more explicit description of this local Langlands map? Sorry, this Langlands map.
But what could be more explicit?
Maybe something in terms of the different Whitaker models instead of the usual Whitaker models.
I definitely don't know any such assertions, and I don't think that's the right. I don't think that's. There are questions to ask in that sort of direction. I know the kind of thing you're saying, but I don't think that's exactly the right setup for those kinds of problems.
So for which class of stacks core can be described as bounded below objects and particles?
Wait, you mean as?
Oh, it's not. I thought that's what you're using here. Oh, sorry. I mean, as a sub. Sorry, what do I want to say? I'm not sure. Or maybe to intersect. Sorry, but here you don't just need to know they map to bounded below category, you need to read and to know that they map to core, right?
No.
No?
I need that eventually, but yeah. So in other words, my argument that.
Argument I did not for the
Okay, so okay, maybe I
because
didn't.
as far as I understood this with the kind of say both things of something, you construct a map.
Okay, so there were two things. So one was I was kind of trying to say that if you think about geometric Langlands as an equivalence on small objects, then we're done just with this LG course. We didn't need anything else. So this LG course was enough to characterize the geometric Langlands equivalence just by itself. Now what geometric Langlands should say is compact objects here map to this co-nilp isomorphically. But I don't want to just deal with small objects because then I can't do all my functors and I can't prove all my theorems. So I'm rephrasing it this way instead, and it does have some content. But so so let me give a little bit more discussion. So let me say that first that Drinfeld and Gates-Gorey proved that D modules on Bun-G is compactly generated, which is a more serious theorem than it maybe sounds like. And so now what I'm saying is the following. So giving this functor LG to this end co-nilp, this is equivalent to giving a functor from D modules on Bun-G compact to a end co-nilp. So these are the compact objects for me. Just by end extending, that's the universal property of that's how compactly generated categories work. So this is the restriction. God, I'm gonna. My restriction of LG. But now my hypothesis is that.
Oh, sorry. Yes. I understand the question I wanted to ask. So
Yeah.
when is it true that unbounded below objects in core is the same as quadrical?
What is it?
For which steps it's true that bounded below objects in int core are the same as bounded below objects with quadrical?
Oh, that's true for any like algebraic stack with no,
Okay.
no functions.
So nothing specific about Luxi.
No, yeah. The only thing where I would use something specific about Luxis is I really know quasi-co is compactly generated using this like spectral localization functor we wrote down earlier. That's one place where every so often I don't want to lean on general theory and just say I really know that there are enough perfect complexes. It's probably there are more efficient arguments, but yeah, and so I do want to highlight for like arithmetically minded people that somehow, for me, this is like a big miracle. It's a real point of departure versus like the classical theory of automorphic forms. So if you think what this functor is doing, it's recording the data of all the Whitaker coefficients of a D module. Like that's some sort of Kesselman-Schleicher thing, but like this basically knows the data of like acting. Like if you think what the ingredients are is like acting by a sheaf, which is basically the same as acting by some Hecke functor, and then taking the basic Whitaker coefficient, and that's what Kesselman-Schleicher tells you is how to interpret that in terms of some other Whitaker coefficients of your automorphic sheaf. In particular, things like the constant sheaf are sent to 0 under this functor in the case of non-abelian groups. And so kind of this is something, and it kills everything we call like non-tempered or anti-tempered. It sort of passes through the quotient to the tempered part. And so it's really known in classical Langlands program that Whitaker models don't do everything that you need them to do. And there are many serious things to say about this. But what I'm saying is that just by some sort of categorical nonsense, this playing with small objects and big objects and T-structures, you actually don't really need that problem, because just using the Whitaker models, you can actually reconstruct the functor itself. And that's for me, it's a very serious point. It's like, it's a serious point. Like, for example, in like the Farag-Schulze setting, what this is saying is that like there's a Whitaker. Just using Whitaker models, you can uniquely characterize like the local Langlands correspondence, which is sort of a surprising statement if you think about things in terms of their classical formulations.
Sam, I'm sorry, could you remind me what the plus means?
Eventually co-connective objects.
Eventually co-connected, thank you.
Yeah, so cohomologically bounded from below, finitely many homology. Yeah. Yeah. I know, it's just, yeah. Yeah. Yeah, and I guess the content of the existence statement is that compact objects here map into the plus category down here.
So that's the real.
And it's also, isn't it also exactly the opposite of what? Oh no, it's the same as what people usually mean by D plus.
Yeah.
Yeah. Okay. All right.
Other questions? I mean, I can comment that, in fact, the argument that shows that this maps into D plus actually also shows it maps into the bounded derived category. So you don't really need to worry. Okay, great. Yeah. No, but like the difference between these two things are infinitely connective objects, and so yeah. Okay, other questions? Yeah, so yeah, I guess again I want to say this. I really want to emphasize this point that, like, you know, for people who work in p-adic groups, like there's sort of a big role which is played by like the work of Kazhdan-Lustig on affine Hecke algebras, and then that really got reinterpreted by Bezrikhovnikov, who went much further with collaborators also. And one of the real starting points for that subject is, again, that you can really reconstruct everything from the Whitaker model, and you can think of that, like, maybe it's not exactly written in that way, but you can think of that as kind of essentially the same mechanism of playing with T structures and big objects versus small objects, and tells you that that geometrically, that categorically, the Whitaker model somehow has within it a lot more information than it does classically. Suitably understood. Okay, and so now I guess I also want to say just ditto in the Étale and Betty settings. So we obtain these Langlands functors. And now what the geometric Langlands conjecture says is that, you know, it says that these various functors are in equivalence. Let me not write it on the board. Okay, I think that's probably a good stopping point for today. So maybe we should stop 10 minutes early, and yeah, let's leave it there, and then we'll kind of go on next time. So, okay, thanks everyone.